All right, hello everyone. So today I wanted to discuss isomers in this video. So guys, we have talked about isomers before, but today we're going to be talking about some special isomers, and they're called stereoisomers. So first of all, why do we actually need to talk about the separate category of isomers? Okay, so what we've learned so far in our previous lectures, guys, is we have learned what we call constitutional isomers. You might not know this name, but we in general we're talking about isomers. Okay, and what we meant by those isomers to differentiate about the ones we're going to talk about today, those are called constitutional isomers. Okay, so constitutional, oops, sorry about my pen, constitutional isomers. So guys, what are constitutional isomers first of all? Uh, so this is when you have the same formula, and we've done this before. So for instance, let me actually draw simple carbons. So for instance, you got 5 carbons, okay? And this is one way to have 5 carbons in a straight chain. And then the other way would be that we still use 5 carbons, but we only keep 4 carbons in the main chain. And think about this, we remove this last carbon, and instead of this last one sitting on this second last one, so if we number these 1, 2, 3, 4, and 5. What if we take this 5th carbon and then we put it on the 4th carbon? I mean, it is on the 4th carbon. We remove it from the 4th carbon, we put it on the 3rd carbon. So again, the 5th carbon, it's not sitting on the 4th one anymore, it's sitting on the 3rd one. Okay, so now you can see how the two molecules that you have that we are showing here are two different molecules. They're two different isomers. Okay, and to be specific, these are called constitutional isomers. In constitutional isomers, guys, you will see that the attachment for the molecules will be a little different. Okay, the composition is still the same, but the way they're attached is different. Okay, so for example, so just for doing more examples and for this, let's say you got carbons like that in the straight chain, and then you got a bromine sitting here, okay? And then we got a similar molecule, again with 5 carbons, but this time the bromine is still there, but it's sitting on the carbon in the middle. So you see how the attachment are different. Okay, still you got 5 carbons in the bromine, 5 carbons in the bromine, so that's still the same, but the way they're attached is different. Okay, so that's constitutional isomers. This is what we have learned before already. Okay, today we're going to be learning more sophisticated isomers. So what happens here is the arrangement, let's not use the word arrangement, the way the molecule is structured, in the sense that how the attachments are going to be the same. The spatial arrangement of the molecules will be different. So let's take an example. Okay, so you guys see this is a limonene is basically the chemical which gives lemons and oranges their smell. Okay, or so the fragrance that you get, and we can differentiate our senses can differentiate a lemon from an orange based off the smell. And the only difference, guys, between these two molecules are both, so this molecule is present in lemon, this molecule right here on the right hand side is present in oranges. So you see the one on the left, the limonene here, is being called S, whereas the other one is being called R. We're going to be talking about that later on in later videos. But if you see, guys, in the first site, these molecules actually look identical. So you got this 6 carbon cyclic chain, 6 carbon cyclic chain. You got CH3 on the top, CH3 on the top. You got a double bond here. You got double bond here. You got the hydrogens. You got the carbon with 2 more carbons attached, a 3 carbons attachment, and a 3 carbon attachment. So you see how similar they actually look. But if you notice, the way they have been arranged, just things being on the left versus things being on the right, makes a difference. and that difference is big enough for these molecules to behave differently, and even and even our bodies have adapted to differentiate them. Okay, so these molecules do behave differently. Okay, and just because the spatial arrangement. Okay, and since the spatial arrangement is different here, the term which is used for these types of isomers is called stereoisomer. Okay, so stereo does mean space. So stereoisomers are when there's a difference in how the things have been placed on a molecule. Okay, just as spatial arrangement. Okay, so stereoisomers is when you have very similar molecules in the sense that the composition is same, even the attachments are same. So again, if you guys notice, in constitutional isomer, the attachments were at least different. In stereoisomers, the attachments are exact same. So if this carbon at the very bottom is the one which is holding a 3-carbon substituent and a hydrogen, the same carbon is holding the hydrogen and the 3-carbon substituent. Or you can notice the very top carbon has a methyl substituent. Similarly here, you got the top carbon having a methyl substituent. So even the attachments are same. It's just how they're placed makes a difference. Okay, so those are stereoisomers. Okay, now stereoisomers come with a condition. And what is that condition? Is that the stereoisomers are supposed to have a carbon whose all the neighbors are going to be different. Okay, so let's take an example for that. Okay, so let's say you have a carbon, and this carbon happens to have, for instance, an OH group sitting here, and it happens to have a hydrogen sitting here, and then it has a bromine sitting here, and then it has a CH3 sitting here. Okay, now if you look at this carbon in the very center, this carbon, guys, has 4 different neighbors. Whenever you have 4 different neighbors on the carbon, you have the chances of finding a stereoisomer. Okay, and the carbon who has these 4 different neighbors, these carbons are called chiral carbons. So guys, chiral carbons are necessary for you to have a stereoisomer. Okay, so that's a condition. You must have chiral carbons to even talk about stereoisomers. Okay, we will be learning later on, guys, in later videos that there are different types of stereoisomers, like enantiomers, diastereomers, mesocompounds. We'll talk about that later. Right now, we're going to keep it very basic. Okay, so again, this carbon, let me label this with a star. So guys, this carbon right here is going to be called a chiral carbon. So if I draw another carbon and it happens to have a CH3 here, has a hydrogen here, it has a bromine here, and it has a CH3 here. Do you think this carbon sitting in the center is going to be chiral, or the opposite of chiral, guys, is called achiral? So something which is not chiral is going to be called achiral. So here in this carbon, again, what was the condition? The carbon, all the neighbors should be different. For the central carbon, for this carbon, are all the neighbors different? You see a hydrogen, you see a bromine, you see a CH3, but we have 2 CH3s. This will make this carbon achiral. So this carbon is not chiral, so it will not be a stereoisomer. Now, the idea, guys, is what we have is what we call optical activity. Okay, so guys, the molecules that we were seeing earlier on the top, these 2 isomers of limonene, guys, there's a device where we can actually tell so this chemical light passes through the chemical, and the light will either get deflected to the left or to the right. So there are sensors on the opposite side. So guys, this simple experiment will tell us the difference in the molecule. Okay, so if you have if you take this molecule here, the lemon limonene, which is the S-limonene, it will have a different optical activity compared to the orange limonene chemical. Okay, so again, we'll talk later what RNS actually means, but in terms of optical activity. Okay, so when you have a chiral carbon, you might have an optically active or we can also use the word a chiral molecule, okay? Again, we're gonna learn more later on in the videos, okay? So again, let's take some more examples. So for instance, if you happen to have a molecule like this, and there is a bromine, let's say, sitting here, then in this molecule, do we have any chiral center? So that's the idea, okay? So this is the very first carbon. If we know this carbon has 1, 2, and 3 hydrogens sitting on it, so this carbon can never be chiral because it does not have unique neighbors. It has all the hydrogens are same. Okay, on this carbon sitting here, again, it has 2 hydrogens. So again, this is not going to be a chiral center. This carbon sitting here, if you notice this carbon has a carbon on the left-hand side and it has a carbon on the right-hand side. But are those 2 carbons identical? No, they're not. If you see this one on the right-hand side, this carbon is actually a CH3, whereas this carbon on the left, this is a CH2 carbon, so they're different. Okay, and in the bottom you got the bromine. So we got one neighbor on the left, one neighbor on the right, it's this one, and then we got one neighbor in the bottom, and the one which is not shown here is of course the hydrogen. So we got 4 different neighbors that will make this carbon a chiral carbon. So guys, this carbon here is the chiral carbon. Okay. All right. So I hope that is making sense here. So again, we're keeping it very basic right now. Okay. So let me show you a similar example. And again, bromine sitting here in the bottom. Now let's look at this molecule more carefully and let's try to figure out if this carbon sitting here is still chiral or not. Okay. So again, this was CH3. Okay. This is CH2. So let's just label them so that's more clear to us. CH2. Let me rewrite that. This is CH2. Okay, this again here, guys, this is also CH2, and this carbon at the very end, this is CH3. Okay, so now let's see if this carbon has all unique neighbors. So again, the hidden hydrogen. So it has hydrogen, that's good. It has a bromine, that's good too. And then when you look at this carbon, the other 2 neighbors, if you go left, you got CH2, CH3. When you go on the right, again, it has CH2, CH3. Okay. So again, look at the molecules carefully. You might have same neighbors. You just have to be careful, okay? All right, now in this case, will this carbon be chiral? No, it's not going to be chiral because it does not have 4 unique neighbors, okay? All right, and then let me give you another example here. Okay, so we're going to be comparing 2 molecules, and then we're going to be seeing if those molecules are what type of isomers. Are they stereoisomers or are they constitutional isomers? So guys, let's take an example, this one. So again, if you guys notice that the composition for this molecule, we got 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and we got OH and we got an OH. So it seems like they should, for each other, they should be stereoisomers in the sense that the OHs are differently positioned. But if you look carefully, the OH position is actually not the same. Here, the OH, if I count 1 and 2, the OH is sitting on the second carbon. Here, if we count 1, 2, and 3, the OH is sitting on the third carbon. Here, guys, the connectivity is different, okay? So these 2 to each other are constitutional isomers and not stereoisomers, okay? We will be doing more examples on this later in our later videos, okay? All right, so that is it for this video, guys.